All right, welcome back, Contemporary Math. We are in chapter 10a. We are taking a bit of a different direction. So we started in chapter 1, and now we're skipping ahead a little bit, then we'll jump back a bit. So we are going to 10a. This is the fundamentals of geometry. So we're going to start talking about geometry. And so if we start talking about geometry, I don't think we can talk about geometry without talking about this guy called Euclid. So Euclid, give him a 325. And Euclid wrote this book called The Elements. I talked a little bit briefly about what this was in the previous section. So in 1a, when we talked about logic, we talked about these things called axioms. And so we have things in math called axioms and theorems. So theorems are derived from the axioms. So at some point, we have to stop asking those annoying questions, right? And just start assuming that things are as they are. So we have to have some kind of fundamental rule about the way things operate, some fundamental sort of observation about things. And so this is what our axioms are. They are quote unquote, self-evident truths. And so Euclid wrote this thing called The Elements, and it is the second most popular book next to the Bible. So the Bible's the first, the Elements is the second most translated and written book. It was sort of like this thing to translate it from the ancient Greek to the Latin. It was sort of this, what do I want to say? This accomplishment that people would brag about, right? It was a sort of, I can't think of the word now, but here we go. So what are we going to talk about? So Euclid is known because he produced the axioms that give us Euclidean geometry. So there is this thing, if you want to look it up, but if you want to look up Euclid's postulate. So postulate is unproven. So he put forth a sort of rule that he didn't feel like was an axiom. He didn't feel like it was self-evident, but assuming it produced this sort of geometry. And so the geometry that we know, which is Euclidean geometry, this is the regular sort of geometry that you're familiar with, where the interior angles of triangles all add up to 180 degrees. But there are other forms of geometry, depending on how you interpret this postulate. There are basically three sort of ways you can interpret this. One way gives you Euclidean geometry, the other gives you hyperbolic, and the other gives you elliptic. So there are other forms of geometry that we could talk about, but we're not going to. We're only going to stick to Euclidean geometry, which is the common sort of geometry that everyone knows about. And so we start this section off with a bunch of definitions before we even get to any sort of math problems. So we're just putting down a bunch of words. So the first thing to think about would be a point. What is a point? What is my point? Why am I talking about a point? Why am I pointing to the word point? So, how big is a point? So a point is one of those things that is purely conceptual. We could be talking about my pen. We could be talking about the city of Austin. We could be talking about the United States. We could be talking about the entire Earth. We could be talking about the galaxy and so on. We could get larger and larger. We could get smaller and smaller. We could be talking about an ant. We could be talking about an atom. We could be talking about a subatomic particle. So the thing about a point is it's purely conceptual. So if I ask you what size a point has, it really kind of has size. It's a weird sort of thing. And that's my point. So line is formed by connecting 2 points. So we have a point. We have 2 points. We connect 2 points. Okay, so they're talking about along the shortest path possible. So they're saying it's not curving out here, right? So it is a straight line is what that would make. If we want to talk about a line segment, we're talking about a piece of this line. So it doesn't have the arrow. This is going 2 points. It is not going off to infinity. A plane is a flat surface. So we have a line. We have 2 lines. You can sort of put them together. You can create a plane. So this would be the Cartesian coordinate plane. If we make this an X and a Y, Cartesian coordinate plane. And so a line has zero size. If we want to, or a point has zero size. If we want to think about a line, well, it goes on and on forever. So it has but if I ask you how wide this thing is, there is no width dimension, right? This line is as wide as I want to make my font, right? This has a finite length and no width. So I guess this is finite and no width. And the last one, the plane, has both a length and a width. And it's also infinite. Where are we at? There we go. But it has no thickness. It's not coming in or out of the paper at all. So the dimension, so one way we can think about the dimension, it's the number of independent directions in which you can move if you were on an object. Okay. Alternatively, we can think about it as it's going to be the number of coordinates that are required to locate a point. And so if we think about something with zero dimensions, that would be like a point that has zero size, it has no dimensions. There is no direction you can give me if you're on a point. If we think about one dimension, so there is one sort of direction, independent direction. We can go forwards or backwards on a line, right? But these things, one is kind of like the negative of the other, right? They are not independent directions. So we have one independent direction we can go on a line. If we're on a plane, we can go left or right, we can go up or down. So these two things are independent directions. And so we can talk about going two independent directions on a plane. Coordinate. This would give me space. So if I have to give a point in 3 space, this would give me an x and a y coordinate. This would just give me like an x value. This I would need 3 different numbers. I would need an x, a y, and a z, or an ordered triple is what we would say. And a little bit about the metrics. So if we want to think about the metrics that we're talking about, if we want to do distance, distance is going to be 2 points on a line, or the distance between 2 points on a line. So that would be one dimension metric. If we want to think about a metric on a point, there's not a lot of things. There's no dimensions we can measure there. But if we measure one dimension, it's a distance. If we measure 2 dimensions, that would be like an area. And if we're we can take surface area on 3-dimensional objects. So we can take distances on 2D objects, right? We can do distances between 2 points in a plane. We can do area on a 3D object. We can do distance on a 3D object. So we can always go down a dimension. But if we're doing one dimension, we can't do like volume on a line, right? So don't try to go the other way. And so maybe a little bit, if we're talking about maybe distance, about areas that would be like meters squared, meters cube. You could replace that with any sort of thing. Meters to what, inches maybe would be the U.S. standard custom. Standard custom. We're talking about inches, a single dimension. Would be inches cubed, inches squared would be double the two dimensions. Sorry. And we'll talk a little bit more about what that means in a minute. Okay, so an angle is formed by an intersection of two line segments. That's what these, I pulled these definitions out of the book. I think they might have changed a little bit with the rendition, but they still work. It's still the same thing. And a vertex is the point. So when you have an angle, you have two line segments, they are meeting at a point. This is the vertex. The point is the vertex. Degree is the most common measure of an angle. So if we want to talk about degrees, the way we can think about degrees, if we go around a full circle, if we're going around a semicircle, it's a half a circle, that is degrees. If we're doing a quarter of a circle, that's like that perpendicular sort of line. If you think about dividing a circle into a quarter, it's going to give you a circle into 10. It's going to give me 36 degrees. If we do a right angle, we do a straight angle. They're talking about a straight line. So these are pretty common definitions. Hopefully you know most of these, if not all of them. The next thing is perpendicular. That's when two line segments. Our axis is a perpendicular axis. If we're talking about the Cartesian coordinates, we are doing a square coordinate system, so everything is perpendicular in there, right? Parallel. So a line or line segments in a plane that are everywhere the same distance apart. Another way to think about this is they have the same slope, right? They are traveling at the same rate. They're never going to intersect. Intersect. There we go. In plane geometry. So a circle. If you think about a circle, the first thing we do, if you go draw a circle, you're going to reach in your bag, you're going to poke yourself with that thing called a compass. But once you get done bandaging up that wound, you're going to put down, that little pointing thing is going to go down, and then you're going to set that compass is just going to set, and you're going to put that pencil, so you're going to put down your center, and then you're going to set your pencil, and that's going to determine a radius. So there are two things that we kind of need to determine a circle, a center and a radius. So the book defines it as all the points the same distance, or I use the all points equidistant. Point from a given point. So it's all the points equidistant from a given point. From a given point. The radius is the distance that we're talking about. The center is the given point that we're talking about. If we want to talk about the diameter, all the way across the circle. Diameter. So a diameter is twice the radius. I'm going to draw my diameter that way, but if I drew it this way, If we go halfway across the circle, it's a radius. Go all the way, it's a diameter. Going through the center. Now we want to talk about polygons. So a polygon is a closed shape in a plane made from straight line segments. So we're talking about any sort of like closed line segments. It's a polygon. A regular polygon is a polygon that has all the same length and interior angles are the same. So we can have, there is a diagram, I believe it's 10.2 in the book. I could be wrong. Yeah, I didn't write it down here. There's a diagram in the book with a lot of regular polygons. But if we're talking about a regular triangle, a triangle that is all the same length and size, that is known as an equilateral triangle. That is a regular polygon. Each interior angle is going to be 60 because when we add them all three up, they have to be 180. Isosceles is also a really common thing to talk about. So that's a sort of triangle that looks like this. We know these angles are the same, and we know that these sides are going to be the same. A right triangle. It is a triangle that has a right angle. It contains a 90-degree angle. If we want to talk about perimeter, that is going to be the distance around an object. So we're going around an object in a singular dimension. We're talking about distance. Length or distance. There is one dimension there that we're measuring. It is a 2D object, but is it a 1D one dimension metric? So if we're talking about circumference, that is just a perimeter of a circle. So we can think about it as walking around the circle. If I want to walk around the perimeter of my land, I'm going to walk around the outside of my land, right? And so we use this sort of in our everyday language. I'm hoping it's not going to be the most confusing thing, hopefully. But some people, I guess, have difficulties with it, so I shouldn't speak too firmly. So the circumference is the perimeter of a circle. If I want to know the formula for it, a lot of people are going to try to tell me and that's all good and dandy. Two of the radius pi d, we can say C equals pi d, right? Okay, so if I want to do something, one thing I can do is make the diameter equal to 1. And if I make my diameter of my circle equal to 1, and then what C is 2 pi d, not 2 pi d, pi d, sorry. I know the circumference should roll out to pi. If I make this diameter right here a 1, some unit metric of 1, so I make that my 1. The ratio of this to my circumference should be pi. So my circumference should equal to pi if I roll the circle out. So if I like cut it, nip it here maybe, and just roll this thing out, should be pi. So this guy Archimedes, and this is another ancient Greek guy, he was noticing if I put so he is doing a rectangle inside of a circle, and he's doing a rectangle on the outside of this circle. And so one of them is inscribed, one of them circumscribed. So if we look at the diameter here, the one circumscribed is the one on the outside. So if we're going 1 by 1 by 1 by 1, we are going 4. So he's just doing 1 unit. So it doesn't say what the unit is. It could be inches, it could be centimeters. It could be your own thing is what he's doing. So it's just like some kind of unit that he's making this thing. This is the 1. My diameter is equal to 1. In the inside, I don't want to talk too much about the inside, but there's another one where he's inscribing. So what he's doing is actually making the diagonal of this thing. And we'll talk more a little bit later, probably about how he's finding that. Or some of the information I give you later might help you find how he's finding that. I don't want to go into too much into how he's doing that, but there are ways to find this diagonal and to find if the diagonal is 1, how long is the side of the square. So he's finding that, and he's finding the inside perimeter, and he's finding the outside perimeter. And this is one of the ways that we can find what pi is. So he's starting with a square, a regular square. The next thing he's going to do is go to like a pentagon and go to 6-sided, 7-sided. And so each time he's going to increase the sides of the polygon. And the more and more that he's increasing the sides, the more and more it's going to start looking like the circle. And so he's getting at the circumference is going to be pi here. So he's kind of sandwiching this circle between 2 regular polygons is sort of what the approach is. Okay, so we want to talk about the areas. So areas are 2-dimensional metrics. And so if we talk about a rectangle, people can tell me they'll probably just say width or base times height. Either way, that's good. So what does this mean? We'll go maybe back to what a regular square would look like. So if we have a 1-inch square, a 1-inch square, or 1 square inch. So if I have something that is not a square, so now we're going into a rectangle, and what sort of the area of a rectangle means. Let's go 3 by 2. That looks good. 3 by 2. Let's keep it simple. So if I have something that is 3 inches by 2 inches, and I got my inches marked off, you might notice each one of these little things is going to be 1 inch by 1 inch. So what this means, and if I'm doing this, I'm going to go 2 by 3. That's going to give me 6 inches, and I have to say they are square inches. And so I should really put maybe the measurements here. When I put inches times inches, it's going to give me square inches. 2 times 3 will give me the 6. And so what this means is that I have 6 of these little squares that are 1 by 1 inch in this thing. That's another way to think about it. Is like, how many of these little 1 by 1 inch squares can we cram into this thing? And I know I'm not drawing it completely straight with the ruler, but each one of these things should be a square. Should be equal in measurement, right? Okay. But there are 6 of these little things that I can put in there. 6 square inches. Okay. So that is a rectangle. Now, if I want to talk about a parallelogram, so a parallelogram is going to look very similar to a rectangle, except the sides are sort of parallel. So it could look sort of like, try to draw it, sort of like this. And the book has a really good picture, so if you want to go look at the book, I won't blame you. But what we're arguing here is that we can drop this sort of diagonal here. We can kind of cut this piece along here. And maybe if I overdo it in red, I'm going to cut this piece off right here. And I'm going to come put it over here. And I can make an argument about these angles of the parallelogram. This angle and this angle are going to add to 180. And that this angle and this angle will add to 180, so that when we add them up, we'll get the 360 interior degrees of a 4-sided figure. We could divide it into triangles and kind of prove that. But if we look here, this is the angle 1 and this is angle 2. That's going to give me my 180. That's a straight line. I can prove the same thing over here. This will give me 90 degrees. So I've essentially, what I've done is by piecing this thing back together, I've made it into a rectangle. It's got 4 90-degree angles, and I can do a little bit of math to prove that with what these angles are going to equal, and looking at the angles of these triangles. So there are a few arguments that I can make here that I'm kind of glossing over, but if you're looking at these angles, you can demonstrate this sort of thing to yourself, right? Okay. Each one of these 4 sides should be. Let's turn it off. That's interrupting. Okay, so this is basically going to be a rectangle. So if we have a parallelogram, we're going to drop this sort of thing. We're going to call this our height, and we're going to call this our base. So our area is still going to be base times height, but now our height is going to be this diagonal that is dropped from one base to the other. We're not going to look at this side, right? Okay, so that changes a little bit, but it's still base times height when we're talking about a parallelogram. We just have to do a little bit of Frankensteining and turn it into a rectangle. Okay, so triangle is the next thing. So if we want to know how to do a triangle, we start with a rectangle. And if we start with a rectangle, I'll go ahead and give you the area of a triangle is 1/2 base times height. And the most obvious thing to do, if we want to half this area of a rectangle, is to sort of go down this diagonal and take half of it. And so this is my base. Well, I guess this would be my height when the way I've been drawing it. Let's keep it by the convention. So this is my base. This is my height. If I want half of it, there we go. I have a half of my rectangle there. Makes a triangle. So that's all good if it's a right triangle. I can get a half base height. If it's not a right triangle, something like this maybe, have a base, but I got to do the same sort of thing right here. I got to drop a perpendicular and make this my height. So my height goes from my base to my alternate angle. And so I want to prove that this sort of thing is still 1/2 base height. And so if I'm looking here, this is like my base. Ooh, let me do subscripts. Let me redraw this on the next page. So I'm looking here at my triangle. It is not a right triangle. So I drop a perpendicular, and I basically, what I'm doing is I'm making 2 right triangles now. So this is my height. So I have a half base 1 times height will give me the area of the first triangle. And I have a half of base 2 times my height will give me the second triangle. Let's say together this is going to be my base. The entire thing is my base. I'm dividing it up into sort of like base 1, base 2 happening here is what I'm doing. So my area overall is going to be this area plus this area. Or I could do a half. And you might notice this is sort of, this is going beyond probably this class. This is going into too much algebra. Oh no. But this is a half and a height, a half and a height. I have this common factor of a half and a height. And I can do the opposite of distribution. I can do some factoring. I can factor that thing out. If I distribute, I get back to this thing, right? But my base 1 plus my base 2 is just another way to call my base. So this is still a half base height. So that's where I'm getting a half base height out of this thing. So if it's a right triangle, I can just do the diagonal. If it's not a right triangle, I can divide it up. I can drop a diagonal, make it 90-degree triangle, and now I have a half base height still. So triangle is still area equals 1/2 base times height. In any larger sort of quadrilateral or polygon or quadrilateral that's just a weird shaped quadrilateral that's not parallelogram, we're going to divide it up into a triangle. We're going to divide it up into two triangles, and we're going to do the area of smaller figures, right? That's typically our approach. Is if we have a larger figure, we're going to divide it up into smaller sort of figures, right? And we can find the area of these things. Okay, with that said, how do we find the area of a circle? So I think a lot of people will probably just tell me right off the bat, area is pi r squared. So that's interesting. But I think we can get at it a little bit more. And this goes back to that's it. It was Archimedes, right? Archimedes proof. So he put like a regular square inside one. We can put a like pentagon, 1, 2. We can put a pentagon and inscribe a pentagon. And we can keep putting more and more sides, 2, 3, 4, 5. Let's see if I can do this. 6. We can put a 6-sided figure. We can put a 7. We can go 8 to an octagon. I don't want to keep drawing this thing, but if we look at this area right here, each time this little margin of error is going to shrink a little bit more and more. And we're going to get closer and closer to our circle. And so this was the sort of thing that Archimedes noticed. And so what I want to think about is a circle that's got a really, really infinite number of sides, right? Our polygon is essentially going to have an infinite number of sides. And so we're going to make some assumptions about affinity that we really can't get to in this class yet, but also realize if we really think about this thing, have a circle, have this figure, it's got a lot of sides, and we're not going to draw it with all the sides it has, but let's just have a lot of sides. I talked a little bit about this, but we can divide larger figures up into triangles. Pretend like this has a lot of sides. I know I'm only drawing one. 1, 2, 3, 4, 5. I can't even count. 3, 7. I'm only drawing 7. So, pretend like it has a lot. I come here and I snip like right down here, and I roll this thing out. It looks like a bunch of triangles. I have an infinite number of triangles here. And now I want to think about the dimensions of these triangles. The height of each of these triangles is going to be the radius of that circle. So we're going from here to the end of the circle. One of these is the height of one of those triangles. This is the radius. If I want to think about this thing, a bunch of bases. Base 1 plus base 2 plus base 3 plus base 4. And I can have that same sort of argument when I was doing the not right triangles, when I was doing the areas of those. It's still going to be my whole base. If I add them all together, that's going to be the circumference of my triangle. So if we areas are half base 5. Base is my circumference. Is my radius. Circumference is what? 2 r. And so I can plug that in instead of my circumference. Have a half times 2 is going to simplify out. 1/2 of 2 is just 1. Have a pi and an r is going to give me an r squared. So this is sort of where we can derive pi r squared by looking at a circle as being an infinite sort of sided figure, right? So we're using the area of triangles to get at the area of a circle. And so, like I said, I maybe had to gloss over some things about like an infinity, but there we are. I think maybe it was, I think there's this. If there's anything I want you to take away, I don't want you to like memorize how these things are proved, right? But I think it's important to show you, like, in math, we're deriving one thing from the other, right? We have this information that we can use, and we're building upon it, and we're piecing these things together, sort of like a puzzle, to get to new information by making basic assumptions. So if you want to go back and look at the elements, that's where he's laying down those axioms. That's where he's laying down those assumptions about geometry. Very basic things about points and lines and how they intersect and things of that nature is what he's laying down in Euclid's Elements. And so a window consists, we're getting our first example, so now we're going to actually do some real math and crunch the numbers, or what you would like to consider real math, I guess. That all that other stuff I would consider the more pure math, to be honest. But I guess we all have our opinions, and let's get to this. So a window consists of 6 foot wide by 8 foot tall rectangle cap by a semicircle. How much trim is needed to go around the window? How many square feet of glass would be required to replace the window? So they're asking us two things. So how much trim is needed to go around the window is one of the first things. And it consists of 6 foot wide by 8 foot tall. So this is 6 foot, 8 foot. So the first thing, if you're given a word problem, I would draw a diagram of some sort. Okay. And so this is one of the things, depending how you draw your picture and interpret it, I would give you probably credit either way. But the first thing I want to do is how much trim. So how much trim is sort of like asking what the perimeter of this thing is. So in mine, I went 6 foot, 8 foot. And then I got to know what this thing is. I got to know how to calculate this. So this is going to be a half a circumference. Circumference, yeah. And so we got to figure out what the circumference of the circle is. So if we want to know the circumference of the circle, we could do 2 pi r or we could do pi d. So it's either 2 pi r or it's pi d. Here I would just go with the diameter. So we have the diameter of this thing is going to be 6 foot. So if we want to know the circumference of this thing, it should be 6 pi. Okay. So if we want to know how much trim we need for this thing, how do I do it? I did not consider this piece in there. So what I did, I went from 8 foot here. I'm going to go 6 foot here. I'm going to go another 8 foot. And then the last thing is this thing right here. So I know one circumference is 6 pi, but I don't want to go a full circumference. I only want to go half, which is going to be 3 pi. And if I did this, I got somewhere around 31.425. And if they're talking about trim, I want to put some sort of unit on this. So I am talking about a single dimension. So I am talking about that in feet. So that is the trim. The other thing is the area here. Shoot, where I'm giving you stuff away. So how much square feet of glass? So here they're even giving you it away with by saying how many square feet. So we know square is a 2-dimensional metric. So we need to measure this thing with 2 dimensions. And it should be an area. So if they want to know how much glass, we need to know the area of this thing. So the area of the circle, let's call this A1 and like A2. So if I want to know my first area, the area of this rectangle is just going to be base times height, 6 by 8. It should be 48 not inches, feet squared is what we're doing here. So that's the area of the first thing. If I want to know the area of the second thing, I know it's going to be pi r squared, so pi My R here is going to be half of 6, so that should be 3, and I have to square it. And so that's going to be the area of a whole circle. I don't want a whole circle. I want a half of that circle. So I want to do a half pi, and my R here is 3, and I'm going to square it. So this is going to be a half pi. I'm doing 3 squared is 9. So this is going to be 9 halves pi is another way I can write that. So if I'm looking at the area overall, I'm going to do that 48 feet squared, and I have to add that to that 9 halves pi I just found. And if I'm adding these two things together, I should be getting somewhere around 62.137 square feet. Okay, so we're doing two-dimensional objects. So now the next thing, example 2. You are trying to paint a wall in your room. The wall consists of a cathedral-style ceiling where the rectangular portion of the wall is 12 feet by 9 feet high. The wall comes to a peak 3 feet above the rectangular portion. How many square feet of paint will you need? Okay. So this one, they're only asking us one question, which is how many square feet? So this is an area problem, is what this is hinting at. We want to cover this with paint. We need to know the area for paint. So if this is 12 feet by 9 feet high is what this is telling me. This is 12 feet by 9 feet. And then it tells me something about this diagonal being 3 feet is what that whole sentence is talking about here. The wall comes to a peak 3 feet above the rectangular portion. Now we want to know how much paint we will need. So there are 2 areas we need to consider here. There's the area of this rectangle, and then there's the area of this triangle. So the first one is base times height is 9 by 12. The second one is going to be 1/2 base height. So it's going to be 1/2. My base is 12 and my height is 3. And if I calculate these, this should give me, I believe, 108. This one should be giving me half of this is 6 times 3 should be 18. So if I'm looking at this, I'm adding 108 and 18 to find my total area. And if I'm doing that, I should be getting 126 square feet. Okay. And then we'll start talking about 3-dimensional objects. A one-block city park is bounded by 2 sets of parallel streets. The streets along the block are each 73 yards long, and the perpendicular distance between the streets is 65 yards. How much sod should be purchased to cover the entire park? Okay, so they're asking how much sod. And if we want to cover it with sod, what they're wanting to know is how many square feet are we going to cover. So they want to know if this is 73 yards and that this is 65 yards is the information that they're giving. So this is 73 by 73. 73. If we want to know the area of this object, it's going to be base times height, or 73 by 65. So this is that parallelogram. So this should give me 47, 45, And we're talking about two dimensionals, so this is square yards, or yards with the square. Okay. So for three-dimensional geometry, so I want to jump and just use this page. So in the book, there is this table 10.3, and I want to just go through these formulas real quick. If I'm being honest, I don't expect you to know how these things are derived right here. This one is above. I don't know. I'm not going to go over how sphere surface area is or the volume area. I will give these to you if I ever ask you to solve anything with this sphere. So that is a little above and beyond. But if we go back to a cube, so this is extending on what we know about areas, right? So if we do an area, that's a two-dimensional metric. If we want to do three-dimensional measurements or volumes, this is sort of the way that we're going to do it. So if we have a 1 inch by 1 inch by 1 inch, we will have a 1 inch cube. And so this is going to be sort of like the unit that we use to measure volumes and things. How many little 1 inch cubes can we get in there? Same sort of thing. If we have a, I don't know, 3 by, let's do 4 by 2 by 3. Let's do 4 by, I don't know, 2 by 3. So let's try to draw these things parallel. No, horrible. So imagine a sort of strip running through there, and this has 4, 1, 2, 3. Horribly drawn. I am not. So horribly drawn. But if we were looking here, if this is a 3 by 2 by 4, this is 3 by 2 by 4, 824, you would count 24 little inch cubes in there. So there would be 24 little inch cubes that could fit in this thing. And then the last one is sort of like, we're taking a circle, and this is sort of like that extrusion thing. We have the area of a circle, and now we're stretching that area of a circle another dimension called height. And so this, you might notice, is the part that's the area of a circle, and we're adding another dimension to make it a cubic dimension. And so this is where the volumes are coming from. If we want to look at surface areas, I'm ignoring sphere again. 6L squared, we have a face. We're looking at the faces of these 3D objects. So 6L squared is coming from, we have 6 of these little, I can't speak anymore, squares that are L by L. Similar here, we have 6 faces, but we have one here. So if we look at this front face, this is length and height. If I'm looking at this top face up here, this is what? Width and length, or length and width. And then this side face over here is going to give me the width and height. And so I have a top and bottom that look the same. I have a front and back that look the same. I have a left and right that are going to look the same. And so we're adding length and width plus length and width plus length and height plus length and height plus width and height twice. We're adding each of these twice, and so this is where this 2 is coming from. Okay. If we want to look at the faces on a right circular cylinder, we have one face here, and we have another circular face here. So these are going to be pi r squared if we think about the area of these faces. So there are 2 of them, so we're going to add pi r squared plus pi r squared is where that first pi r squared is coming from. The other thing, if we roll the cylinder out, So we snip the cylinder down the side here, and we roll it out. This is going to be our height. This is going to be the circumference of our circle, or we have 2 pi r. And this now is a rectangle, so this is 2 pi r times h to get the area of this thing. And so that's where this 2 pi r h is coming from. Okay. So back to this problem. A water reservoir has a rectangular base that measures 20 meters by 35 meters and vertical walls 10 meters high. At the beginning of summer, the reservoir is at capacity. At the end of the summer, the depth of the water is 2 meters. How much water was used? What are they telling us? Draw a figure. That's what I would start with. So I know this thing looks like 20 by like what, 35. And then I want to talk about the height of this thing. So I know it's got like something like this. Maybe not the best drawn picture. But I got a base and I got a height here. So the base is rectangular, 20 by 35. It has a vertical wall that is 10 meters high. At the beginning, it's at capacity. At the end, the depth of the water is 2 meters. Okay, so how much water was used? So there are a few ways you can do this. We know the whole thing is 10 meters. We know that in the end it was 2 meters. So if we wanted to figure out how much we used to begin with, we could go 20 by 35 by 10. This would give us the initial. And then we could subtract it by what? 20 by 35 by 8, which would give us the ending. Ooh, not 8, 2, sorry. Getting ahead of myself. So this is one way you could absolutely do it. If you want to do it that way, that's fine. But the other way, if you're drawing your figure, maybe you might notice, is that this is going to give you 8. And so this, even if you do the math here, this is the same sort of distributive property. We could go 20 by 35 by 8 will give us the same amount that was the amount used. It's a horribly drawn picture. There it is. This is the height. This is the base, length, and width. Okay, so this should give you 5,600, and it should be cubic meters. Okay, so the next thing, we did one with the volume. Now we're going to talk a little bit about one with a surface area and volume. Are we? Yeah. Which can hold more soup? A can with a diameter of 5 inches and a height of 8 inches, or a can of a diameter with 8 inches and a height of 5 inches. So the first thing that they're asking, draw a diagram. So we have 2 cans. So the first thing they say is a diameter of 5 inches. So if it's got a diameter of 5 inches, it's got a radius of 2.5, and it's got a height of, what are they saying, 8 inches. The other one So can 1, can 2 has a height of 5 inches, and it's got a diameter of 4, which means got a diameter of 8, which means the radius is 4. So these are the two sort of pictures that we could draw. I guess you could have started with drawing the diameter and then drawing the radius, but I jumped right to the radius because that's the number we're going to need to find our area and volume. So if we want to find the volume of the first can, the volume is pi r squared h. So we do pi, we do 2.5, we square it, and we multiply by h, which is 8. This should be giving me 157.08, and I'm talking about cubic inches, or I can do the inch cube is also acceptable. So that's the volume of the first can. I did not leave enough room for y'all, did I? Okay. The surface area, so this is can 1. Is going to be 2 pi r squared. So I go 2 pi, I'm doing r squared, plus 2 pi RH. So 2 pi RH is 2 pi 2.5, and then we got to do by 8. So plugging this in, we should crunch this thing and this thing separately. And so if we crunch this all together, hopefully we're getting 164.93, and we're talking about square inches here. Or you can say square inches. Okay, so I didn't leave enough room. Here we're going to need to do can 2. So the volume equals pi r squared, so pi r squared. So my r here is going to be 4 this time. My height is 5. And if I'm crunching this, this should give me 251 cubic inches. And I got 251.33. Okay. I'm looking at this thing, and I want to look at the surface area. So the surface area of this thing is the same thing, 2 pi r squared. So I go 2 pi, I go r squared, plus 2 pi RH, looks like 2 pi, my r is 4, my h is here 5. So I'm doing the same formula, plugging in the numbers. This should give me 226.19 square inches. And now we want to talk about, after doing these calculations, we want to talk about something about scaling laws. And so we want to think about this thing. Let's say, I don't know, start with something that's, I measure 1 inch out, and I want to triple that. So 1 multiplied by 3. 1 inch to 3 inch. So if I'm doing a single dimension, I'm going to end up tripling this thing. I'm measuring 2 dimensions. Tripling. If I want to think about 2-dimensional metrics, if I triple this thing in 2 dimensions, I'm going from 1 inch squared, and now I'm going from 3 inches by 3 inches. I'm going to 9 inch squares. Huh. And so what we might notice is if we have 1 dimension, it's going to triple. But if we have 2 dimensions, it's going to go up by 9. And if you want to think about how do we go from what, 2 dimensions, and we're tripling it, how do we go to 9? What's happening is we have 2 of them. We have 3 being squared. And so anytime we do dimensions, and you could probably guess, if we do 3 dimensions, we're going to go from 1 by 1 by 1, like this, 1 inch by 1 inch by 1 inch, and we're making that into dimensions by dimensions by dimensions. We're going to go from 1 inch to 2, and we're going to go to, you can probably guess it, hopefully the pattern. When we have 3 dimensions, if we're going 3 by 3 by 3, we're going to have to go and cube it. So if you multiply it by a factor, or if we're doubling, right, double would be times 2. In a single dimension, we would multiply by 2. In 2 dimensions, we would have to multiply by 4. And in 3 dimensions, I didn't write it out here. In 3 dimensions down here, we would have to multiply by what, 2 to the 3rd or by 8. So you're going to always have to exponentiate things to whatever sort of dimension you have, right? You're going to multiply that many times. So we have to do sort of thing called dimensional analysis, or the scaling law, I guess is what they're getting at here. And so we want to think about these things. Doubling. So I've already talked a little bit about doubling. By what factor has your waist increased? So if you measure your waist, you're going to measure your waist probably in inches or centimeters. And so that is a single metric or single dimension. By talking about the dimensions of these things. So that's a single dimension. How much more material would be required for your clothes? So if you're talking about clothing, you're going to talk about square footage of cloth. So this is going to be double. I'm going to say double 2 dimensions. Double dimension. And by what factor has your weight increased? So if you're talking about your weight, so your weight is actually a factor of both gravity and your volume, but we're just going to be talking about the sort of volume here. So this is going to be the 3-dimension example. And so if we're doing a single dimension, if we're multiplying by 2, we're just multiplying by 2. So this is going to double. If we multiply by 2 dimensions, then we're not doubling again. If you double your size, if you double your height, you're going to quadruple the amount of cloth that you need for your clothes. And if you double your height, that's going to be 3 dimensions. And it's going to multiply by a factor of 8. So your weight's going to change by a factor of 8. You're going to be 8 times heavier. I saw a demographic that like failed to sort of take this into account, and it showed like different height of women, but they failed to take into account that the volume would be multiplied by a exponent of 3 of whatever the heck the change was. So if they doubled the height, the person would be like 8 times larger in their little demographic, and their little, not demographic, their little graph that they had. I'm trying to think of a word now. Their graphic is what I'm trying to say, not demographic. So 3 dimensions will get you by a factor of 8 if you're doubling things. Surface area to volume ratio. Oh man, I can't believe I didn't even fill this thing in to you. So if we're doing a ratio, we're comparing 2 things with a division sign. And if they tell us surface area first, we're going to do surface area,
and you're going to divide that by volume.
So if you want a surface area to volume ratio, we had an example earlier with 2 cans. 2 cans, Sam? Okay, no. For example 6, which can would be better to produce? Would you want a large or a small surface area to volume ratio to save money on production? So for producing these things, we want to think about making aluminum cans with food in them, soup for our families. So our surface area is going to be the material that we're making it out of. This is going to be the aluminum that we're talking about. How much aluminum do we need? The volume is going to be the amount of product. So we want the most amount of product for the least amount of packing material. So we want this to be small. We want this one to be big. And if we have a small number over a big number in a fraction, oh man, big denominator, small numerator means overall this fraction should be small. So we're looking for a really, really small ratio. So we're looking back to can 1. Do its surface area over volume. I believe that gave me 164.93 over 157.08. And hope y'all are verifying this with the calculator and working along with this. Double check my numbers, and if you ever figure out I'm wrong on anything, always feel free to comment. We're going to do the same thing. And if I do this, you might notice this is a bit larger, 1.44. Okay. And so for some things, like if we're going to produce these cans, we want to produce something with the least amount of aluminum to the most amount of food that we can put in that can. So that would give us this one, can 1 would be the smaller ratio. It would be more ideal for the production of this thing. So there are cases in which you might want the smaller ratio. We want maybe to think about other cases. So if you want to cool food quickly, the best way to do that, and you probably, if you've worked in the food surfaces, you probably know you want the most surface area to volume. So you want the most amount of surface area to volume. So this would be the larger ratio. So if we were trying to cool these things, we would put it into can 2, right? Another thing, if you were to try to make some kind of medication, right, and you wanted it to be super reactive, you would want to maximize your surface area. So you'd want the larger one. So there are scenarios, depending how you propose them, you might want one over the other, right? You might have to add some context to what you know from the real world to get there, but we can do that. So I will see you in class pretty soon. Also watch 10B, and we will be there. All right, see you soon.